Before we can build a simulation model, we need to first understand the basic concepts. Our manual simulation will be used to help us understand the simulation process. Consider an ice cream store. This is a server and a line of customers. The server provides ice creams. Customers buy ice cream one by one. Each customer leaves after getting the ice cream. This is a queuing system. If we run an ice cream store, there are several things that we need to consider. Apparently, we need to have an ice cream machine and a cash register. We need to hire someone to deliver the ice cream. We need to have space to accommodate customers. Is there any VIP that must be treated with priority? We have a few measures to evaluate the performance of the ice cream shop. Most importantly, how many customers do we serve? How long do they have to wait? Are the server busy enough? So here is a simple flowchart for this queuing system. Customers arrive at random times. They are served immediately if there is nobody in the line. Otherwise, they need to wait to be served. The line above the customer served box indicates a possible queue. After that, they depart from the shop. Each box represents an event. If you stay in the ice cream store and take notes of the customer, you can record a number of events over time. Customer arrives, customer in the line, customer served, customer leaves. Here, the recorded event is up to 15 minutes. Your textbook has observation of up to 20 minutes. We may reorganize events into the view per customer. This allows us to easily see when each customer comes and leaves. We consider each customer as an entity. Using the previous table, we can easily see 4 customers were served in 15 minutes. We do not know when the 5th leaves the queue, so the 5th one is not counted. To calculate time in system, we just need to subtract the arrival time from the leave time for each customer and take the average of them. This time in system is also called flow time or cycle time. The waiting time is the time between arrival and the surface, so we subtract the arrival time from the surface time, and then take the average. Another measure for waiting is average number of waiting customers in the queue. This measure is a time persistence statistic. Let's explain it in the next slide. Time persistence statistics is also called time-weighted statistics. Basically, we multiply each parameter value with its duration of time and sum them together. In the case of total waiting time, we can multiply the number of waiting customers with the duration of time. The graph helps us understand how many people are waiting in the queue at any moment in these 15 minutes. So here is how we calculate the total waiting time. As a result, the total waiting time is 15.17 minutes. Again, that's the total time that all people spend in the queue. Here are more performance measures. By dividing total waiting time by observation time, we can get average number of waiting. Number of waiting and number in surface together are work in process, WIP. Utilization is the busy time of the server divided by the total observation time. In this case, since the first customer comes at time 0 and the server has been busy always, the utilization is 100%. The ice cream store shop example is similar to the example in Chapter 2 of your textbook. In this textbook example, a number of blank parts pass through a drilling press machine to be drilled. Apparently, the server is a drill press. The customers are similar to the row of blank parts to be processed by the drill press, the server. We have analyzed a simple queuing system. Now let's see a few very common terminologies in simulation. The first one is entities. Entities are objects in a system. Each entity has one or more attributes. A system has variables that are applicable to the whole system. Our system has many resources to provide service. For example, the server in the ice cream store is a resource. It is quite common to have queues in a system. Finally, statistical accumulators are observed results of a system. We analyze the system performance with these statistical accumulators. By looking at the observation date, we can have a few educated guessing for the simulation output. If customers come too frequently, the queue may become too long. If the average inter-arrival time is less than the average surface time, then there is always a queue because customers are waiting to be served. Next, let's analyze it more formally. According to the queuing theory, the ice cream shop is a simple MM1 queue. The first M describes the customer arrival. M is Markovian. It means the arrival time satisfies Poisson distribution. If the arrival time are Poisson distribution, then the inter-arrival time satisfies exponential distribution. The second M describes the surface time. It means the surface time satisfies exponential distribution too. The last one means one server. We can analyze this simple queue and get exact analytical solutions. There are three categories of performance measures. Counts are counting the numbers, for example, the number of people served. Observation-based statistics are also called tally. An example is the cycle time, that is, the average time it takes for an entity to be processed. Time-persistent statistics are called dstat. An example is the average number of people waiting in the queue. The key to tell whether a statistic is a dstat is whether it is averaged by the observation time, also called run length. Now let's consider the drill press example in your textbook. If you prefer, you can consider it as the ice cream shop too. They are similar conceptually. We present these performance measures in mathematical equations. The first one, total production of entity, is a count. Average waiting time and maximum waiting time are observation-based statistics, that is, tally. Time average number of parts is a time-persistent statistics because it is averaged by the run length. It is a dstat. This is expressed in the integral format. We calculated it with discrete values for the ice cream shop. Maximum number of parts is the longest queue length. It is a tally. The cycle time, as discussed earlier, is a tally too. We have calculated utilization before for the ice cream shop. Here we present the equation for the utilization with integral. It is averaged by the run length, so it is a dstat. There are other possible measures that we may find later in the arena running result reports. Think about the ice cream shop or the drill press example. We may have noticed that the observations are centered around events. When an event happens, attributes, variables, or statistics will change accordingly. Common events include arrival, surface, and departure. To simulate the process, we need a calendar to keep track of the events. In the calendar, we list the events in the order of time. The events happens at discrete times. That is why it is called discrete event simulation.